My name is Dana Habeeb. I'm an assistant professor in the Department of Informatics at Indiana University. Today, I am presenting our paper investigating and validating on-body temperature sensors for personal heat exposure tracking. I'm presenting this paper with my co-authors, Dr. James Clawson, Arash Zakeresfahani, and Zebulon Holtz, who are also affiliates of Indiana University. Personal heat exposure tracking is an important topic, especially when we consider the relationship between extreme heat and public health. We see in the United States that more people die to extreme heat than all other natural disasters combined. But this is not just a U.S. problem. We see with the most recent climate assessment report that extreme heat and heat waves is one of the top climate crises that will be impacting communities across the globe. As such, it's important for us to understand our vulnerability and risk to extreme heat. Cities, and specifically urban residents, are more vulnerable to extreme heat because of what's known as the urban heat island effect. The urban heat island effect occurs when we see temperatures are hotter than the surrounding rural areas. These hotter temperatures are due to how we are designing and building our cities. We're basically displacing natural vegetation and replacing it with impervious surfaces such as buildings, roads, and parking lots, and all that goes to increase our temperatures. Not only do we see temperatures differential between urban and rural, but we also see that temperatures vary dramatically within the built environment. This makes it very difficult to measure and assess our individual personal heat exposure. Ubiquitous sensing technology has been used in the built environment in order to better assess and map hyperlocal environmental exposures. For this research project, we're interested to see the capability of wearable temperature sensors to accurately measure near-surface air temperatures for individual personal heat exposure. We began this research project by conducting an extensive literature review. From this literature review, we wanted to see what were the most common sensors used in the research, where people were wearing the sensors on their bodies, and we also wanted to see what different themes emerged from the literature. One of the main themes we identified was vulnerable populations. There are many indicators for vulnerability, including environmental exposures, sensitivity, and adaptive capacity. Many of the papers examined vulnerable populations, specifically examined that for occupation, looking at outdoor workers such as those in the construction industry and in agriculture. Others investigated athletes as well as elders, who are some of the most vulnerable people and individuals in our communities to extreme heat. This research project compares 4 commonly used off-the-shelf temperature sensors. It compares them across 5 on-body locations and in 2 urban settings. From left to right, we are using the Hobo MX2301A, hereafter referred to as a Hobo handheld, the Kestrel D3F3, which is orange, the Hobo MX2202A, which we will refer to as the Hobo pendant, and the iButton 1923. We're comparing these in 2 urban microclimates, a parking lot and in an urban forest. We installed in situ sensors in both of these locations and are using them as ground truth measures, where we are co-locating our wearable sensors with these in situ sensors in order to calculate bias scores, which is the difference between wearable sensors and the ground truth in situ sensors. We installed these on the campus of Indiana University, which is part of a larger sensor network. To conduct our study, we performed a series of tasks, which were performed in the same order. To begin, we first acclimatized in each of the microclimates. After acclimatizing for at least 17 minutes, we stood next to the in situ sensors. In the parking lot, we began facing the sun. Then after a certain amount of time, we turned our backs to the sun. Next, we walked around the sensors for a set amount of time. We then transitioned to the next microclimate. For the forested area, we stood by the sensor, but we did not face the sun or turn our back to the sun since we were in the forested area. But instead, we stood by the sensor for twice as long before continuing to our walking task. On the left, you can see a table listing the bias scores averaged across individual tasks and users. From this table, we can see a positive bias is exhibited across all sensors and across all on-body locations and microclimates. When examining the 2 different microclimates, we can see that there's a significant difference between both the forested area and the parking lot, and the parking lot had a bias score that is 3 times higher than the forested area. We also see that the main effect of sensor technology were statistically significant. All 4 of our sensors are significantly different from each other, and the Hobo with the Hobo pendant having the highest bias scores, and the Kestrel had on average the smallest bias scores. All sensors are significantly different by microclimates as well, and the Hobo pendant elevates its bias scores dramatically when in the parking lot area. We wanted to investigate how these sensors were actually performing during the study trial. In order to do this, we created a radial stacked bar chart. Starting at number 1 and moving clockwise, this graph averages all trials that began in the parking lot, which is number 1, and then ended in the forested area. Number 1 represents when we were standing by the sensor facing the sun in the parking lot. We then moved to number 2, which is where we turned our back to the sun. Then at 3, we transitioned to walking, and 4, we ended our trial in the parking lot. We transitioned to our forested area where we acclimatize as necessary and start the study again. We stand by the sensor for a certain amount of time, and then we begin walking. You can see from the very beginning of this study, when we are facing the sun, all of the on-body sensors start to increase their bias scores and begin overheating. We see a maximum cumulative bias score reach 25 degrees Celsius, reaching its maximum right at the beginning of walking. And then we see a gradual decrease. When looking at the sensors individually, the hobopitten exhibited on average over a 10 degrees Celsius bias in this parking lot. We also mapped the trials when we started in the forested area and transitioned to the parking lot. One thing that we saw was our bias scores looked very different for the forested area. And what this is really showing that these sensors seem to be overheating, and there's a significant lag effect that's occurring from sensors that are overheating. We also examined on-body location and found that the on-body location of waist had the lowest bias scores. And we saw that shoes was the on-body location with the highest scores, but only for the parking lot. Those shoes exhibited the highest bias scores in the parking lot. When examined in the forest area, it actually had one of the lowest bias scores, demonstrating a strong interaction effect with regard to where the sensors were being worn and the context of microclimate. The unreliability of these wearable temperature sensors in areas of high impervious surface and direct sunlight is problematic for the research community, investigating real-time heat exposures for urban populations. Essentially, the sensors are failing to record accurate measures in the areas where they are most needed when it comes to measuring urban heat stress. Areas with large amounts of impervious surface and direct exposure to sunlight are conditions which increase individuals' heat exposure. There are next steps that we can take to improve these sensors, but they need more investigation and prototyping. Researchers should understand these limitations for wearable sensors, especially since they're predominantly used in the research community. Thank you so much for listening, and I look forward to fielding any questions you may have about our work.